welcome to the dynamics tutorials. So with this problem, we have a system that's starting from rest at t is equal to 0. Our system contains this pulley P. The pulley has this rope that's going around it, and then it's attached to this mass here at B. So the pulley's starting from rest. It starts with an angular acceleration of 0.05 t, and we need to find how far B moves in that first 2 seconds. We need to find the velocity of B at 2 seconds and the acceleration of B at 2 seconds. So first off, we just need to find all the angular quantities for the pulley and see what the pulley's doing. So we're going to take our alpha and evaluate that at t is equal to 2 seconds. And so we'll plug in 2 here in our 0.05 times t, and we'll get 0.1 radians per second squared for alpha. And then look, we got to look back at alpha to see whether it's a function of time or not. So alpha is not going to be constant, so we can't use an integrated expression. We have to set up a differential equation. So our differential equation is d omega dt is equal to alpha. Substitute in alpha for angular acceleration, and then we'll have to separate variables, so we'll multiply through by the dt. Now we have d omega is a function of t dt on that side. So we can integrate this, look back at our problem statement for our limits of integration. We're starting from rest at t is equal to 0, so omega is 0 to omega, and t is going to be 0 to t. We don't want to run this to 2 just yet because we want to get a function in case we need to use it later. Integrating and then plugging in, we get omega minus 0 with these limits, and then we get the 0.0250 t squared minus 0, plugging in the limits here. So we can clean this up and plug in our t is equal to 2, and we get our omega of 0.1 radians per second. It's just coincidence that the 0.1 radians per second squared here is the same number as the 0.1 radians per second that we get down there. That's not a general result. And then we'll set up a differential equation for our angle. So we'll say that d theta dt is equal to omega. Again, separate variables, plug in our limits of integration, integrate, and we get omega is equal to 0.0667 radians when we finally plug in that t is equal to 2. Then from those angular quantities, we can go back and get our acceleration, our velocity, and our change in y position. So for our acceleration of b, it's just going to be equal to the tangential acceleration where the pulley is leaving the wheel here. The tangential acceleration has to be the same, otherwise the rope would slip over the pulley. So that tangential acceleration for rotation about a fixed axis is just going to be alpha times r. So we plug in our alpha, we plug in our radius of 0.250 meters, and we get 0.0250 meters per second squared for acceleration at b. And then our velocity at b is just going to be the same as the velocity at point P where the rope leaves the wheel. That velocity for rotation around a fixed axis is omega times r. So we plug in our omega and we plug in r, and we get our VB of 0.025 meters per second squared. Sorry, 2.0 meters per second. Again, just a coincidence that these two values are equal. And then for our delta y is just going to be the angle that we move through times the radius. That's going to give us the circumference that we're moving past. And so whatever that circumference is, that's going to be the amount of rope that we spooled off of the pulley. So that's going to be omega r. So we plug in our omega, plug in r, and then we get that value, 0.0167 meters. And if we want to convert it, apply a metric prefix, we can get 16.7 millimeters. Thanks for watching.